Hello, this is Pete Cacioppi. I'm Chief Scientist at Analytics, and today I'd like to give you a brief talk regarding building prescriptive analytics solvers with Python. So before we dive into prescriptive analytics, let's just discuss the range of tasks for which Python is often used. So as a scripting language, Python is great for exploratory programming. IPython is really a state-of-the-art tool. IPython is a supercharged Python interpreter. And this is great for analyzing data using snippets of code or for writing trial and error code to learn about libraries or writing trial and error code for testing out certain ideas that you might want to use in a more production-oriented environment. Closely associated with exploratory programming is what I'm calling demonstrative programming. This is where you use Jupyter Notebook to create Python-based demonstrations. So if you're not yet familiar with Jupyter Notebook, this is really one of the exciting things about the Python ecosystem. It allows you to present live code or functional code along with formatted text and graphics. And you can represent data tables in a clean way in Jupyter Notebook. So this is also a great data analysis utility of Python. Python is also a strong contender for glue programming with deployments and integrations specifically. As you go into the world of prescriptive analytics, specifically, you talk about things like rapid prototyping. So this is where you have a business problem and a data instance appropriate to that business problem. And you're trying different programming techniques to see how you can solve the business problem. So you might try out mixed integer programming directly, or you might try constraint programming. You might try some combination of heuristics and optimization. And that sort of trial and error work would be done at the scripting level. So you would write a short Python script that would implement one algorithmic strategy, launch it against the data set, and see how it performs. So the final step of evolution, the next step beyond rapid prototyping, what I would call mature code. So this is where you build code that's ready to deploy. It's robust code. It's self-documenting code. A lot of times, specifically my point here is that making code ready for deployment is oftentimes that is coincident with the goals of making code that's also easy to share or easy to archive. So to be more specific, what are we talking about when we're talking about achieving code maturity for prescriptive analytics? So I've organized some goals here. I've listed out some goals. I've organized those goals from the most general to the most specific. So the top level goals would be sort of best practices for mature Python programming in general. And then the goals down near the bottom are things that are very specific to prescriptive analytics or mixed integer programming. So some basic Python stuff is you organize your Python code into a package. A package is just the name for a term that Python uses for essentially for a library. Packages are typically themselves archived in a repository. This is sort of a file structure idea that there is usually ancillary files associated with the package, and so the repository can store the package itself and also the ancillary files that support the package. This is a big thing in Python and also really in modern software development in general. This is specifically the idea that you should incorporate testing into the development process. So we're sort of bridging from things that are expected in Python to things that are useful for prescriptive analytics with this bullet point. From the Python side, a Python package is expected to have a suite of testing codes. So along with the production code that's in the package, you also have testing scripts that exercise the package and ensure that the package code behaves in an expected fashion. So this maps nicely onto a requirement of mature prescriptive analytics in general, in that it's always a great thing to have sample data for your prescriptive analytics engine. And it's also a nice thing to have a test suite to verify current functionality of your analytical engine so that as you add functionality, you can make sure that the pre-existing functionality doesn't break. And that's the general idea behind continuous integration. And Python is a great language to support the general concept of continuous integration. So as we're moving down the list here, I think a good way to think about a prescriptive analytical engine is that first and foremost, it presents a solve function. So it presents a function that takes a data instance that's representative of a particular business problem, determines whether that there is a feasible solution for that data instance, and if so, creates an optimal or near optimal solution. So this is sort of the core of an analytical engine will be the solve function. Now, in order to document that solve function, in order to describe it well, probably the most important thing is to carefully define the input and the output schemas. So now you could define the input and output schema, and you could define the input and output schemas purely through code comments. What I'm going to show today is how you can use the TICDAT library to document the input and output schemas programmatically. So let me just sidebar a little bit and talk about TICDAT. TICDAT is an open source data library created by Analytics, designed to promote good programming practices for prescriptive analytics. So essentially, you can think of TICDAT as an example of benevolent self-interest, because TICDAT also serves as the production API for the Analytics cloud platform. So people in the operations research community are free to use TICDAT without any relationship with Analytics at all, purely for the purposes of building more robust and more mature solvers. But a solver that is built with TICDAT, according to the template that I'm demonstrating here, is a solver that's deployment ready for Analytics. So like I said, TICDAT allows you to programmatically define schemas and to include defining data rules for those schemas. And then with those programmatic definitions, the solve function can then be made robust in as much as the solve function can, as its very first step, validate that its input is an appropriate data instance. So we'll talk about that a little more specifically in a minute. And our final bullet point here is I strongly encourage business groups or even just individual programmers to follow a consistent pattern for representing data tables inside Python. So this is sort of the first challenge you're going to encounter if you're going to try to do mixed integer programming work in Python, is that your code is going to be interacting with tabular data. It's going to be receiving tabular data, writing tabular data. You need to have a pattern for how to represent a table in Python. Now, I recommend, and TICDAT supports, two approaches. One approach is the most straightforward, the most simple approach is to represent a data table as a dictionary of dictionaries. Now I'll show specifically what that means in a minute when I jump over to a code sample. But the dictionary is a basic sort of workhorse of Python, and as you become experienced with your Python development, the idea of embedding a dictionary with a dictionary will not seem very strange to you. That's a very natural way to represent a table in Python. I also think dictionary of dictionaries is most closely maps onto the examples presented by both Gurobi and Cplex, and I think there's good reason for that, in that people coming from the dedicated mixed integer programming languages, those sort of one-off languages that do nothing but mixed integer programming, I think those people will find it easiest to read the dictionary of dictionary data structures. I also think dictionary of dictionaries maps closely onto the way that mixed integer programs are rendered in mathematical literature. That said, you can also use the pandas data frame object. So pandas is itself a whole nother open source library completely independent of TICDAT. Pandas is really a massive library. It's probably the most widely used data library in existence. But the downside with Pandas is that it's fairly advanced, and it wasn't really designed necessarily with mixed integer programming idioms in mind. So that said, if you want to use Pandas, I have some great Pandas examples on TICDAT, and you shouldn't have any problem using Pandas with TICDAT, but I still think that dictionaries of dictionaries is the most natural approach. So let's jump over to some code here and see all this in action. So this is the diet example, so the standard example everyone knows and loves. And I've made a repository that implements the diet example as a package that's meeting the milestones that I discussed in the previous slide. So the root directory for this package is example-diet. You can see that by storing this package, by storing this repository in GitHub, it renders nicely. You can study it through a browser. The README file looks nice. Now, if you study the file structure here, this is where all the work is really being done in this repository. This is the diet directory. The diet directory is itself a package directory, in as much as this diet directory is recognized as a package by Python. The reason for that is that it contains an init.py file. Now, in principle, in practice, the init.py file can be empty, but I strongly encourage you to populate the init.py file, and you can use the init.py file to specify the public components of the package. So at a minimum, the package should contain the input schema, the output schema, and the solve function. Now, before we jump into the specifics of how that is implemented, let's look at the testing section really briefly. So the first point I would like to make is that with a typical Python repository, the testing section is up here as a sibling directory to the package directory. I like to put the testing directory inside the package directory, even though that's slightly unusual. I don't think it really leads to any confusion, and it also makes it a lot handier to access the data files, your testing files, right? So this is sort of idiosyncratic to prescriptive analytics, is that as part and parcel of your test suite, you want to store data instances. So that means you're going to have a directory that stores data. So makes sense to put that inside the testing section. And here in this example, I only have one data instance, so there's only one file. I'm storing that file in a .sql format. So this is a type of SQLite file that's easy to create with TICDAT. This is a SQLite file that has only data row records and no schema records. And the reason it doesn't have schema records is it doesn't need them, because TICDAT knows how to create the schema once you've defined a data factory. So this is just one area in which I think TICDAT could be very helpful to you, in that TICDAT lives on top of the directory, on top of the libraries that do the actual file I/O. So instead of you having to study the SQLite package or the CSV package or the Excel package or the ODBC package, you can just use the TICDAT package, and the TICDAT package knows how to call those other more low-level libraries. And then here's an example still within the test section here. Here is the testing script file. So oftentimes the testing section has more than one testing script, but for this simple example, it's just one testing script. And if you want to study this in detail, then feel free to study it online. Specifically, you'll probably want to study this unit test package, which is a standard Python package that supports unit testing. And again, I like putting the testing directory inside the package for prescriptive analytics, because that way it makes it easy for me from within IPython to programmatically find my data sets, because the data sets are inside the testing. Now, As one final note, if all of this testing stuff seems like a big headache to you, but you also recognize that it's important and useful, this is one more argument, one more opportunity for me to plug Opolytics. The Opolytics cloud platform is great for adding GUIs. It's great for deploying your code in a production environment. But if you're an Opolytics client, you can also hire us to help you build the testing section, even though the testing section is strictly speaking part of the engine code. That's an easy part of the engine code to outsource to somebody that's focused on it and excited about testing. So now we get to the fun part where we can look at some mathematical code. So this is the diet example, again, rendered. This time we're implementing it as the guts of a package. So this particular example is using Gurobi, and it's also using TICDAT. Don't worry so much about this freeze me code. You can study that function in the documentation for TICDAT if you want. This is the workhorse of TICDAT. It's a class called TICDAT Factory. With that class, you can define a schema and add rules to a schema that's already been defined. So here I am defining a schema. Again, a schema is just tables with fields defined for the tables, and the fields organized into primary key fields and data fields. You can think of a schema as being sort of like an access database with no rows, but with defined tables. So in this case, the input schema for diet is these three data tables: categories, foods, and nutritions. As you see here, when I'm listing out the field names for each table, I'm organizing the field names into two subgroupings. The first subgrouping for primary key fields, the second subgrouping for data fields. Don't be scared off by the database terminology. A primary key field can also be thought of as an identifier field. In my experience, everyone that's done mixed integer programming work understands the concept of primary key fields, even if they've never learned the terminology. And as an aside, that's also true down here when I'm saying add foreign key. Everyone I've ever talked to who does mixed integer programming work understands that child tables connect to parent tables through specific fields that have to match up. That's all a foreign key is. So let's walk through again very quickly. Categories and foods are sort of primary top-level tables, so they only have the single primary key field. Categories has two data fields. Foods has one data field. Nutrition quantities is a child table. It has two primary key fields and one data field. And then each of these primary key fields, this primary key field matches up to this field in the parent table. This one matches up to this field in the other parent table. And those two relationships are defined here when I'm adding the foreign keys. And then to flesh out the schema completely, I'm specifying the data types for all the data fields. The default data type is a non-negative, non-infinite number with no integrality restrictions. And that's appropriate for all of the data fields in the schema, except for the max nutrition, which allows infinity. Now, you might think that this whole section is just a lot of extra work. And I guess I would like to point out that it's really not that much extra work. I mean, I feel like TICDAT's made it pretty easy for you. And I think by specifying these things, you make your schema more readable. But the big payoff is that you make your solve function very robust with dirty data. And I really think it's a big mistake to overlook the reality of dirty data. For whatever reason, for miscommunications, for failure, in the integration code, there's a million reasons why you end up with dirty data, just plain old user error. But dirty data is a fact of life, and it's not a great thing if your solve function throws a cryptic exception when it encounters dirty data. And it's an even worse thing if your solve function runs and returns a puzzling result because it failed to stop itself and to give a good error message when it encountered dirty data. So a great thing about the TICDAT library, and this also dovetails with the Opolytics GUI, is that the TICDAT library and the Operalytics GUI, the Operalytics platform, all anticipate dirty data and provide a good infrastructure for identifying dirty data. So specifically with TICDAT, the first thing the solve function does is it does a sort of a high-level sanity check on the argument itself. So that's this line of code. You're just looking to make sure that you're given a valid data object that has the correct table and field names. And the next step is to ensure that the child tables match up correctly with the parent tables. And then the third step is to check all the data fields and make sure they have sensible values. So these three steps right here, particularly these two steps here, in my experience, can save you a lot of pain down the road, and they're well worth this fairly minimal effort expressed in these, 10 lines of code there. Now, of course, defining the solution schema is fairly similar to defining the input schema, except you don't really need to worry about dirty data in the solution schema because you're creating the solution. Now, if you wanted to be picky, you could point out that really a solution for the diet example could consist of just this one table that tells you how much food to buy, but it's also nice to have some ancillary data. So I'm including a table that shows how much nutrition gets consumed, and I'm also including a parameters table with which you can store the total cost. This parameters table is an example of how you would specify a data table that has data fields but no primary key fields. And if you look at the example-netflow on the Operalytics GitHub page, you'll see the converse of that. So the netflow example, the multi-commodity netflow example, has tables that have primary key fields but no data fields. So both of those cases are well handled by TICDAT. Now moving on to this solve section. Before I talk about the solve section, I would like to encourage you to look at the Garobi diet example and compare that code to the code, what is this, 55 lines of code here, 45 lines of code here. My point being that this solve section is very similar to the Garobi solve, and that's not by accident. I think the reason why that's so is that if with a well-chosen, well-designed library, it's not that difficult to upgrade something that's more like a proof of concept code into a production code. Although personally, I use TICDAT at sort of every stage of the game. I mean, I haven't used it with integration with passing data back and I haven't used TICDAT for glue programming per se, but I've certainly used it for everything else, for exploratory programming, demonstrative programming, rapid prototyping, and production code. TICDAT's handy for all of those things. Now, assuming you understand the Garobi example really reasonably well, I'm just going to focus on some TICDAT specific things. So we already talked about how these three lines of code really protect your code from dirty data. Here, this is an example of how a data table in TICDAT is by default represented as a dictionary of dictionaries. So this dat object is roughly equivalent to an access database. The categories attribute, because dat is consistent with the data factory schema, then dat will have an attribute called categories that represents the categories table. And of course, it represents it as a dictionary of dictionaries. So you can call the items function, which is common to all dictionaries, to walk through the keys and the values of the dictionary. And in this case, each of those values is itself a dictionary of the data row. So the inner dictionaries all have keys min nutrition and max nutrition because those are the fields of the categories table. And a very similar logic applies here to the foods table, except that is only the one data field named cost. Here we see the dictionary of dictionaries being used with a data table that has a multi-field primary key. So again, this is the equivalent of an access database. Here's the table. Here I am looking up a row in that table where the food field matches is equal to F and the categories field is equal to C. And here I am looking up the quantity value for that data row. So again, this is the sort of thing that it might look a little intimidating at first, but I think you'll get up to speed on it pretty quickly when you play around with it a little bit. And I think if you look at the examples where I use pandas, I think you'll perhaps agree that pandas is even a little bit more complicated than this. I think like anything else, there's a learning curve, and I think this is a pretty quick learning curve to get used to dictionaries of dictionaries. Now let's talk a little bit about, we showed how you can read data from a data table with Python. Now let's talk about how you can create an empty data instance and then populate the rows in that data instance. So this line of code here creates a tickdat object that's consistent with the solution factory. So that's like creating an access database that has all the tables and fields of the solution but doesn't have any of the data rows populated yet. Now to populate the data rows, that's what's happening in this code here. And it's a little trickier than it looks, so let's pop over and look at perhaps a simpler version first. So again, if you, by default, tickdat represents data tables as dictionaries of dictionaries. So the most straightforward way, perhaps the most obviously comprehensible, but also the most tedious way to populate data with tickdat is to simply assign the data row to a dictionary that has the right field names for that table schema. So that's what's happening here and here. So buy food is itself a dictionary. When I'm referring to buy food, brackets F on the left-hand side of an assignment statement, Python, when you're assigning, that's the way you assign to a dictionary in Python, and Python, when doing dictionary assignment, will create the value for that dictionary if it's not present. So this is what I'm doing here is effectively creating the data row, and then I'm setting that data row to this dictionary that has the right field names. In this case, there's only one data field, but still this is me doing it in the most simple way possible where I use a full dictionary. Now, Python or tickdat also has some overrides to make that data writing a little simpler. You could also assign directly to the data field that you're interested in. So this is perhaps a little more readable than what you just saw. tickdat has the overrides that when it's doing this assignment, tickdat recognizes that, hey, if this row is missing, I need to create that row in order to assign to this specific data field. Now, if there was more than one data field, when it was creating a row this way, it would use the default value for that field. So default values, some people, I personally like using them a lot. Some people don't like them so much, but tickdat supports them, and I think it's useful with this idiom. Now, when you're looking at the buy food table and the consume nutrition table, you might ask yourself, gee, is this little snippet really necessary? I mean, there's only one data field. Shouldn't tickdat be smart enough to recognize that if I'm assigning a value to a row in the buy food table, it's only possible to assign that value to one place? And in fact, tickdat does have that override as well. And that's why this code can be written this way. This is just like this, except it's missing, except when I remove this section that's technically unnecessary. So those are three different ways that you can write data back to a data table in tickdat, and feel free to use whichever one of those is most readable for you. So thanks for your attention. I think this covers all of our main points. Feel free to contact me. I look forward to any sort of discussion on this topic.